Hi everyone. Today I want to share with you some thoughts about impredicativity, which is ImpredicativeTypes is a feature released in GHC 9.2 that I'm really quite excited about. This is the result of maybe a decade, more than a decade. 15 years of on and off work by a bunch of people. I actually have only sort of a small part to play, but it's the big advance was a paper at ICFP. I guess it was 2020 by Alejandro Serrano and collaborators. There's going to be a link in the description, and it really sort of opens things up and allows us to use this feature. So let's dive in. So I'm going to not be using the Haskell language server in this video because that doesn't support 9.2 yet, but I have 9.2 installed on my system. And so I could just GHCI in here, and then we're going to experiment a little bit with it. So I'm going to turn on ImpredicativeTypes. By the way, this :set I, the I here means that this extension only affects the interactive context. So it's not going to affect when I'm going to start looking at this trees up here. Okay, so now we've turned on ImpredicativeTypes. And what this means is that we can infer places when a polymorphic or a type variable in a function should be itself a polytype. So what do I mean by that? Well, actually, I went too quickly. Let's just turn on GHCI without turning on ImpredicativeTypes, and we can see where we run into problems. So I can make a list here, and I can have a bunch of things in the list. Let's say we can have +1 and -2 and I don't know what that's going to do. I don't want to do that. -2 -2 is going to parse weirdly. Okay, so I can do that, and then I can ask what's the type of funds, and it's going to be some list of functions. And that's fine. I can have a list of functions in a functional programming language, so that's all good. If I try let ids equals, let's say, the list containing the id function twice, I can do that too. And what's the type of ids? Well, it's a list of functions a. But what's strange about this is that the choice of what the a is has to be made once at the very beginning. So if I look at let's see, how can I do this? No, if I do it the way I was going to, I don't think that would work. Let me just see what happens here. I think I know what's going to happen. So if I do let head ids of 5 and then head of tail of ids on x, I think this will work. Yes, that does work because I'm using ids twice here, and so it can get specialized to two different types. Here it's going to specialize to integer arrow integer, and then here it's going to specialize to car arrow car. So that's all good, but there are other scenarios where this isn't good. So like for example, if I say let f equal head ids in f5 fx, we're going to not get an error. Oh, why is that? That's because it's regeneralizing. I don't want it to regeneralize. How can I stop GHC from regeneralizing in this way? It really does like to regeneralize. If I say f arrow return head ids, that won't generalize. And then now, if I say f5 fx, we're going to get an error. And so actually, this is even a worse error than usual because it's mentioning the internal type any. The idea here is that if I turn on, let's see, print explicit for alls, and if I look at the type of ids, the for all a happens outside of the list. If I wanted that for all a to be inside the list, well, that would require impredicativity. That's what impredicativity means. It means having for all types sort of in places that are buried within other types. When we're not impredicative, it means that all of the for alls are sort of out at the top or sort of in to the left or to the right of arrows. So that's what we have without ImpredicativeTypes. Let's look at what we can do with them, or let me show another sort of problem here before I go into ImpredicativeTypes. So if I give it a type signature, if I want this to be a function that really contains a bunch of polymorphic functions, and then I can say ids equals list of id, illegal polymorphic type. Perhaps you intended to use ImpredicativeTypes. So indeed I do. Let's turn that on now. And now that line is accepted. And we say, oh, yes, that's no problem. I can ask what's the type of ids. It's this. If I do this trick earlier, if I say f is return of head ids, then I can say f5, fx, and oh, blah. Why does that happen? That really shouldn't happen. I will need to stare at that for a little bit later and figure out why that happened. I don't think that should happen. I think that might be a strange bug because this feature is new and we're still experimenting with it. What this does allow me to do, though, is it allows me to have types like this. And you might wonder, well, why do we ever need things like that? So let's go to the more drawn-out example that we're going to have up here. So the idea in this example is that I'm going to make a tree type. And my tree is going to contain data at the leaves and also at interior nodes. That's not really all that important. That's just the particular design of tree that I want to have. And we want to be able to show these things easily, so let's derive show here. I'm going to want to be able to create these trees quickly and easily. And so the way I'm going to do that is using the arbitrary feature in quick check. So let me import quick check up here. And then I can say down here, instance arbitrary. So I'm going to go through this bit a little bit fast because I'm going to have maybe another video on quick check. Today is not the day for that video. But here in an arbitrary instance, it allows me to define the arbitrary function. And then the arbitrary function allows me to sort of randomly generate one of these things. So I'm going to use sized here, where gen is going to take an int. Sized allows me to sort of have this decreasing parameter. So let's do this. And then gen of the size, well, gen of 0, I want to have a way of bottoming out. So it's going to be leaf arbitrary. And then gen of something else is going to be frequency chooses things according to some distribution. So one of the time we will get a leaf, just like we have for the 0 case, arbitrary. And then 2 of the time, I tested this before and it works reasonably well. 2 of the time we're going to get node, followed by a recursive call, but we're going to decrease the size. So we're going to have n div 2. And then let's see, and we're going to have an arbitrary bit of value here. And then we're going to have another gen of n div 2. So we'll sort of use up our size here every time we recur. Oops, I need to close paren. And then this, okay, let's see, does that compile? Let me try to load trees.hs. Yes, hooray. And does it actually work? So I can say generate an arbitrary tree of int. Oh, look at that. That's a nice arbitrary tree of ints. Excellent. Okay, so we have that working. Again, more about that another time, but that's a sort of a quick way of creating one of these trees. And ooh, that's quite a nice one. So I'm actually going to just take that and save it here. So we're going to call that tree. It's a tree of int, and it just equals that. Okay, does that still compile? I hope so. Yes, it does. Excellent. But now what I want to think about is here, I can say search through this tree here for an odd number. And maybe if it finds the first odd number, maybe it'll find this one over here. And so if I'm searching through for an odd number, then I'd like to be able to return back some kind of index for where it is. If I just had a list, this would be easy. I'd use a natural number, and that would say how many elements deep in the list is the sort of the element that I want. But right now for a tree, well, gee, I don't really know how to do that. I mean, I could come up with some data structure that stored some lefts and some rights and said here and there, and I could come up with some way of describing it, but that would take some work. I don't want to do that. Instead, really what an index into a tree is I can think of it as a function that plucks out a certain element. And so I'm going to call this a tree index, and I'm going to say that given a tree, it returns an element. So we can say tree A to A. Well, already this is a bit funny, right? Because here I have A on the right, but I haven't set A on the left. But the idea is my index, it should work on a tree of anything. Maybe I have this tree of int and I have another tree of bool somewhere, or a tree of widgets. And I want to use these ints to sort of help me figure out where in the tree of bools or the tree of widgets I want to pluck a bool or a widget out. And so what that means is that I don't want to have this tree index that's returned from some lookup function. I don't want that to be fixed over what type it works on. I want that to be able to work over any contained type. So I really want tree index to be universally quantified this way. But now I realize that not every tree has the right shape. So it's not going to be tree A to A. It's going to be really tree A to maybe A. Because maybe I do some searching in this tree and I find that I have to go left, 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 right, left. But then the tree I do the actual sort of indexing in doesn't have that right structure. So we might end up failing at that point. And so this has to return a maybe. So this is going to be my tree index type. Let's see, how are we doing with compiling? So far, so good. Excellent. Really? I don't need any extensions for this yet. That seems unlikely. But, that's right. We're in GHC 9.2, and 9.2 has GHC 2021. So there's a whole bunch of extensions automatically enabled for me. I haven't quite internalized that yet. Okay, so we have tree index. Excellent. But now I want to be able to look up in a tree. So we're going to have lookup tree. Well, what's lookup tree going to do? It's going to take some predicate on a type A, and then a tree of A's, and then it's going to return a tree index. So we can think of this tree index, again, as a path into this tree, but it's going to be represented as a function. We're in a functional programming language, so let's use functions. And let's see, how can we write lookup tree? So lookup tree is going to take some predicate, I'll call it P, and then that's going to stay fixed the whole time. So I'm going to use this little idiom where I say lookup tree P equals go, and then define go here. And so this makes it very clear to a reader that P is just fixed. I'm not going to change it in recursive calls. So the go function here, this is going to just take tree A to tree index. And let's see here. So what is go going to do? Well, we have to do a case match. And so go on leaf x. Well, if x satisfies my predicate, then hooray, I've done it. I can return, well, not just, I can return, let's see, a tree index. Well, what's this tree index going to be? Well, it has to be a function that sort of extracts out the top element. And so I'm going to use a lambda case here to say case, if this is leaf y, well then we can just return y. That means we have an element at the top of the tree we're looking in. And if I have a node, I'm going to say that that's still some value that's at the top of my tree. I'm not going to really care whether it's a leaf or a node with more subtrees. I could choose tree index to work in a different way, but this is how I want it to work. And so here, if the top thing is a node, then that's also success. I can extract that from the tree. Okay, let's see. How are we doing here? Does this compile? No. So I can use for all here, but I can't use lambda case. Very interesting. Very interesting, GHC Steering Committee. But let me add lambda case here. And now let's see. Okay, so we have something else going on here. Couldn't match expected type A with actual type A1. So A1 is the rigid type variable bound by the type signature for go for all A1, but I didn't write for all A1. I wrote A here. What GHC is very sort of confusingly trying to tell me is that this A up here and this A down here are different, and that's because I didn't bring that A into scope. So if I say for all A here, that will bring this A up here into scope, which means this A is referring back to that one, and this particular error should go away. Okay, good. So now we've gone from red to purple, and what that means is that we have a warning now, and that makes sense. My pattern matches down here are not exhaustive. So far, so good. If I look in my leaf and it doesn't satisfy my predicate, otherwise, oh, well here there's no index to return. My lookup failed. And so really my lookup tree shouldn't return a tree index. It should return a maybe tree index. And then here, this should really be just. Okay, so now here I can just return nothing. Haha, just return nothing. And then let's see, does that work? Oh, no, because I said just and then a lambda. Normally I have to use $, but I'm going to show you we actually have an extension just for this called block arguments. And block arguments means that when there's no other parse, just accept the thing. So it allows me to use constructs like lambda as the argument to adjust. So with that extension, okay, now what happens? Illegal polymorphic type. So what I've said here is I've said maybe tree index, but tree index is a polytype. It's this for all type. So without impredicative types, I'm stuck, but we have impredicative types. So let's just turn that on and merrily go on our way. Okay, now what do we have? Couldn't match expected type tree A2 to maybe A2 with actual type maybe A1. In the expression, nothing. In an equation for go. I wasn't expecting that one. Let me think for a moment. So this actually looks somewhat sensible. Oh, no, it's not very sensible at all. I've gotten this type of go wrong because I made a change up here, but not down here. So let me put it in a maybe. Okay, pattern matches are non-exhaustive. I've looked at leaf, but I haven't looked anywhere else. So pattern not match node. So let's do that. So now we have to look at go. And if go gets a node with a left, an x, and a right, well, let me think. What do I want to do here? I want to sort of look in all of them and then take the first one that applies. And so what I'm going to use is, as I did some, in preparation for this video, I did some poking around to find just the right function. And it turns out that there is just the right function to do the thing I want. And if we look in control.applicative, let's reload. That's going to fail, so I have to comment this out. And if I go down here and reload, now can I ask what a sum is? Does that work? Yes. So a sum is a function from control.applicative, even though it doesn't actually talk about applicative, it talks about alternative. And it has this rather generalized type, whereas it takes a collection of alternative things and then chooses one based on the alternative instance. So it turns out that maybe is an instance of alternative. Let's just see what alternative is. It is a class here. Let's see, where is it? It is a class alternative. And the key thing is it has this operation here, which allows me to take two things of the same type and sort of choose which one I want. So just to show what this does, if I say a sum, or rather, let me start with something simpler. If I say nothing alternative just x, it's going to give me just x. If I say just x alternative just y, it's just x again. So it takes the first just that's passed in. If we have nothing, well, that's just nothing. And then if I have just x and combined with nothing, that's going to be just x. So it returns the first success. So that means that a sum, if we have nothing just x, nothing just y, that will work out, and it returns the first one, the first hit in the list, essentially. So a sum is exactly what we want. So I can say node left x right, so I'm going to call a sum, and then here, well, I'm going to make a recursive call on the left. I'm going to do something here. We'll just put nothing in for now, and then a recursive call on the right. And I know that there's various things that are wrong in this line. We'll fix them all. But this is where we start. And then let's try to load. And let's see. Couldn't match type A0 with tree index. Expected maybe A0, actual maybe tree index. Cannot instantiate unification variable A0 with a type involving polytypes. So what's going on here is that when we're applying a sum to this list, we have to figure out this a sum is very polymorphic. All right, let's take another look at the type of a sum. Now things have fallen out of scope. Let's bring a control.applicative back in, and let's look at a sum. So when we apply a sum, what GHC has to do is it has to figure out what t is, what f is, and what a is for the particular place I'm applying a sum. And the way that it does that is by introducing something called a unification variable. It means sort of a type variable. We don't know what it's going to be. We're going to figure it out as we go. The error that we see here is cannot instantiate unification variable A0 with a type involving polytypes. So it's saying that I don't know what the type should be, but I really don't want it to be a polytype. And the reason for that is that once we allow unification variables to become polytypes, then type inference becomes very unpredictable. this video is getting long enough, so I'm not gonna go off and come up with an example of exactly how it goes unpredictable, but it really does. And so the reason that impredicative types is hard to work with is because of this unpredictability. The idea in this recent paper that I mentioned earlier is that we take a quick look at the argument. So the algorithm is called the quick look algorithm. And what we want to do is, instead of just sort of looking everywhere, we're going to sort of look just at specific parts of the argument. Unfortunately, the quick look algorithm, as implemented in GHC 9.2, does not look at lists. It only looks at applied functions. And so this very eminently sensible call here is actually going to be rejected. And so instead, I have to pretend that I only have bad syntax around and write it out using conses with a nil. Because this quick look knows about. This is just a bunch of functions applied to other things. And so with that change, really I shouldn't have had to do that, but life is imperfect. Now if I refresh, that change really made a difference, because the quick look algorithm is clever enough to do some analysis on this and then do type inference and figure out exactly how asum should be instantiated. So just to replay that a little bit, let's go back to the list syntax. And I can actually get this to work if I say exactly how to instantiate asum. So let's look at asum once again. So I have to say what t is, what f is, and what a is. In this case, t is the container. In this case, a list. So that's t. F is going to be the alternative thing. In this case, it's maybe. And a, the thing that's stored in the maybe, is tree index. So if I tell GHC that this is what I want, then it's quite happy with me. That works. But I really don't want to have to specify that all the time. And so I want to rely on the quick look algorithm to do it for me. But to do that, I have to make this just a bunch of functions applied to arguments. And of course, operators in Haskell are just functions applied to arguments. They're just written in between the arguments instead of all the way up front. So now, having written it this way, I can leave out my explicit type arguments, and all of this works very nicely. Okay, so we still have define but not use, and that's because here, the nothing case, well, what do I really mean? Well, what I want this to do is, if the predicate is true, so if px, then, well, I need to do this whole thing again. So that tells me that maybe I want to abstract that. So that's going to be a root index. So a root index is a tree index. Root index looks in the root of the tree. So this, if I get a leaf x, it's going to return x. And if I get a node like this, it's going to return x. So that's my root index. And now I can simplify this and return just root index. And then here, if px, then just root index, else nothing. And I don't want to have parse error, so let me put that in parentheses. Okay. Aha. So now it compiles. Let's see, does it work? So I want to call lookup tree, and let's look for an odd number in the tree. Well, of course, I can't show one of these polytype things. So let index equal lookup tree odd tree. And so this should be, I go down into one node, and then it looks like it's just the very next node, if I'm counting my parentheses correctly. So it'll be on the left. So if I say index into node of, I don't know, leaf, high, middle, and then leaf by. Hopefully that works. Uh-oh, what has happened here? Couldn't match expected type tree string to t with actual type maybe tree index. Aha, that's because index here is going to be a maybe, but I know that it's going to succeed. So I can say let just index, and I use a little pattern bind there so that index is actually the function. And then here it extracts out middle. Is that what I was expecting? No, that's not what I was expecting. But maybe that's because I was expecting the wrong thing. What's going on here? Ah, there's a bug in my code. You may have seen the bug. So the bug is here, that down here, when I recur, I'm just saying go left and go right. So this succeeded, this go left succeeded actually, but then the tree index didn't get bumped. in any way. So not only do I need root index, I need some other helpers here. So I need left index. So this is a tree index transformer. So left index on a sub index here. So now I can match, well, if I have a leaf, well, that means that there's nothing, right? When I say left index, what that means is that I'm going to take sort of the root of my tree and I'm going to go left. But I can't go left if it's a leaf. So this is the nothing case. And I don't want a warning about not use sub index. I'll get rid of that. So here, left index, if I have a node, left, I don't care. Well, I just have to sub index on the left. And then we need right index, which is another tree index transformer. And then right index, sub index, leaf. This is a little bit boring because it's very similar to the last one. Blank blank right is sub index. Right. Okay, let's see. Does that compile? Yes, good. Okay, so now here, when I go left, so go left is going to return a maybe tree index. I need to modify that tree index. So to do that, I'm going to say fmap left index. And here I'm using the fmap or the functor instance for maybe. And then we want to do that here. Oh, let's do some nice formatting. Always good to format. And then here I'm going to fmap right index of go right. Okay, let's see. Now if I reload, yes, that works. And if I get my index like this, and then I index into here, I get just high. Because this index, if we look at my tree, I had to go left one step, and then that's where I found it. And so down here in my sample tree, I go left one step, and that's where I find it. I could also index into something slightly more glorious. If I have node of, I don't know, leaf blah, and then we'll keep the high right where it is, and then leaf other blah, I still get high because I'm extracting it out from that node. So that's pretty good. I could go even slightly more glorious than this. And instead of just lookup one, I could do multiple lookups tree. So here, I'm going to still need this for all A. This is going to be easier because I've gained some experience. So now I'm going to return all of the indices that are of interest to me. So I could say lookups tree equals go, where go is going to still be a tree A now to a list of tree index. And the structure is going to be very similar to what we had before. If this is true, then I return the root index. Otherwise, I return nothing. And then here, if I have a node, well, it's going to be the same thing, but instead of using asum, I can just use regular old concat. So if I say concat, and then we're going to do the same thing, fmap left index, except now the fmap is using the functor instance for lists, but it's much the same idea, isn't it? So we can do this. Oh, and here I started writing a list just out of habit, but we know we can't use a list because of that very silly bug. So I do that on the left, and then here I can do the same thing. If px, then root index, else nothing. Or else else nil, I should say. And then I can do fmap right index, go right. And then here, that's just the end of my list. And let's see, is that enough? That might be enough. Yes, excellent. Okay, so now if I have my tree here, so let's do lookups tree odd of tree. But we still don't have a show instance, so I can't do that exactly. But I can get its length. And its length is 10. So that means there's 10 odd numbers here. Let's just count. See, is that right? So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 odd numbers. And if I take this lookups tree, so now I have a list of these indices, and I could use those indices to look in another tree. So let's take that tree that I wrote down here. Let's just see what happens. So let's take that, and then how can I get all of the lookups? That's going to be hard because I would love to use $, but $, isn't going to work out so well here. I don't actually see an easy way to make use of this. So let's not, I could spend a while scratching my head, but I'm not going to right now. The bottom line here is that what I was able to do, let me just sort of recap, is that I wanted to have some way of talking about a specific spot in a tree. I could have designed a data structure to do that. There are some advantages of doing that. One would be I could show it really quite easily. But instead of doing that, I wanted to use a functional representation, which also means that I don't have to sort of allocate this structure at runtime and then consume it later, right? I can just sort of build the function as I go in lookup tree. And then I can manipulate my functions here. So there's something nice about this. I can only do this because of impredicative types. And so this has been sort of a quick, maybe not so quick, it's kind of a long video actually, but a not so quick view at the quick look algorithm, which does allow me to do some examination of an argument in order to figure out an impredicative instantiation. I hope this has been interesting. Thanks very much for watching. Bye.